Shalom and welcome everyone. Once again, I want to thank you for joining me in this video presentation. This is Checkpoint Training Bytes. Checkpoint Training Bytes is where we discuss different products, features, and blades. In this module, we're looking at CoreXL and CoreXL technologies, and this is part one of this video series. Once again, my name is Manuel Joaquin, and I will be your instructor. So first of all, let's take a look at the agenda of this module. The first topic we're going to discuss are what are multi-core systems, why multi-core systems were introduced and developed. And then we'll take a look at the need for CoreXL, why CoreXL was introduced. And then we'll look at the different components that make up CoreXL and break down these components. And then we'll put these components together and have a big picture overview of how CoreXL works. And then we'll discuss how CoreXL helps improve performance, what are some of the benefits for having CoreXL. And then finally we'll look at the affinity, and we'll discuss the affinities like the SIM affinity, process affinity, interface affinity, and SIM affinity, and demystify these terminologies. First of all, let's take a few moments to discuss how to improve performance. Hardware vendors are constantly searching for ways to improve performance, while at the same time trying to reduce manufacturing and production costs. Until a few years ago, increasing performance was mainly achieved by increasing the CPU frequency. And so, at the turn of the century, process manufacturers were in constant race to make faster, smaller, and more efficient CPUs. And so the path they took to achieve this goal is to increase the CPU speed, which increases the frequency of how many calculations your CPU can process. But then process manufacturers ran into physical limitations, which are how small you can make and manufacture CPUs. And hence we enter in the multi-core, multi-processor era. And so what process manufacturers did to overcome this physical limitations barrier is they introduced multi-core, multi-processor systems. Will use multiprocessors to simultaneously process data, and so to take advantage of these multi-core systems, multiprocessor systems, Checkpoint had to recreate and redevelop a new code of Firewall. And this new code is what we call the CoreXL code. And so CoreXL was introduced in R65 Firewall. R65 was the first firewall that introduced support for multi-core systems. And at the same time, we needed to update our Linux kernel to 2.6, which is the first Linux kernel that supported multi-core systems. And so in addition to rewriting the Checkpoint code that supported multi-core systems and updating our Linux kernel to support multi-core platforms, customers have to purchase CoreXL product, and CoreXL is a product and feature that I need to install and also license. So before we get down to the CoreXL technologies, let's discuss how a packet is being processed from the CPU before the introduction of CoreXL. Now imagine there's a packet coming in, and it's coming into the CPU. Now the CPU is going to need to process that connection, so it's going to request the firewall code in this case to run its code. And so the first thing that it needs to do is run the FW lock command, which locks the firewall code, and now the firewall code is locked, so it can process that connection. After the firewall code is locked, it's going to do FW chain do, which then means that it's processing that packet. And once that packet is been processed, it's going to then unlock the CPU and forward that packet off on its way. Now this whole cycle is repeated all over again. When another packet comes in, next packet comes in, again it's going to do FW lock, it's going to do FW chain do, and then do FW unlock and forward that traffic on its way. But I want you to know this one thing is that we only have one firewall code, so only one CPU can interrupt that firewall code for processing of packets. But now to clarify this a little bit better, let's introduce a second core into the picture. So now we have two CPUs, CPU 1 and also CPU 0. And so now assume that the next packet comes in, the packet comes into, let's say, CPU 1. CPU 1 is going to interrupt the firewall code, request the firewall to process. So the firewall does the FW lock, which locks the firewall code. Now the packet is going to do the FW chain do, which means it's processing that connection. Now imagine that that packet is being processed by the firewall while another packet comes in, and another packet comes into the second CPU. Now the second CPU is going to need to interrupt the firewall code, but the firewall code is already locked and it's being processed by the primary CPU. and so that second CPU cannot do anything until the primary CPU has finished processing that connection. When it's finished processing that connection, it's going to do FW unlock and forward that traffic on its way, and now the whole process can happen once again for the second CPU. The second CPU can now process that connection. It's going to do FW lock, do FW chain do, and when it's completed, it's going to process that connection and forward that connection off on its way. And so now that you understand the challenges, Checkpoint had to redevelop a new code of firewall that will be able to run multiple transactions at the same time. So how did the Checkpoint solve this issue? Well, let's take a look. Now you see we have two CPUs, and we also have two firewall instances. We have firewall instance 0 and firewall code 1. So these are two instances of the firewall. This is what we call the firewall kernel instances. And so we've replicated the firewall code. This is actually two firewall instances, but they're running the same policy. The same policy is running on actually both of these instances. This is one firewall, and so when a packet comes into the CPUs, the firewall code will lock the code, will request the firewall code to execute, will do the FW chain do, and then unlock the code and do the code. And so that's one component. The first thing that we did is we recreated multiple firewall kernel instances. So we have multiple firewall codes running simultaneously on each of the cores. But in addition, we also had to create another thing. The second thing that we had to create is what we call the dispatcher. We had to make a decision on where to assign the traffic. Will we assign the traffic to CPU 1 or to CPU 0? So this dispatcher is also running on its own CPU. So the dispatcher is running on its own core, and also the NIC traffic is bound to the same CPU that's running the dispatcher. So traffic is coming into the NIC, it's going to the same CPU that's running the dispatcher, and so the dispatcher will process that traffic that came in, and so the dispatcher will make a decision where to process that packet. So it makes a decision where to send it. In this case, it sends it to CPU 1. CPU 1 is going to execute the firewall code where the firewall instance 1 is associated. So firewall instance 1 will look at the packet, will look in a rule base to see if there's a rule allowing that traffic, and if it finds a match in a rule, if it finds a match, it will allow the traffic through. And so the next packet, it comes into the dispatcher. Dispatcher makes a decision where to assign this traffic. It makes a decision to assign it to CPU 0. Since CPU 0 is bound to a completely separate firewall, that firewall will be able to run the FW lock, do the FW chain do, and FW unlock. And so those are the two components. First of all, we introduced the firewall kernel instance, and the second component is the dispatcher. Now we know about firewall instances and the dispatcher. Let's put them together and see how they work. So packet comes in, it comes into the dispatcher. Dispatcher looks in its dispatch table. So the dispatcher has what we call the dispatch table. The dispatch table is where it stores all of the known connections. In this case, it does not know about this connection. This is the first time this connection comes in. The kernel tells us that the connection was not found. Dispatcher makes an arbitrary decision, sends it to the core, which is running the FW worker 0 is running on that core. And so it executes that packet, looks in the rule base to see if there's a rule allowing it, accepts it, and records it in the connection table. So now look at this, is that the FW worker, with its own firewall, will update its own connection table. Once it updates the connection table, it also will update the dispatch table about this connection. Why? Because if the packet was dropped, then it would not update the dispatch table. The packet was allowed, so the firewall worker was telling the dispatcher that it accepted the traffic and updated dispatcher. So the next packet that comes in, the dispatcher will know what to do with it. So now look at the dispatcher. It marks on which firewall is executing. Firewall 0 is executing that connection, process that traffic, and it forwards it on its way. So another packet now comes in. It comes into the dispatch. In the dispatch table, is that packet known? No, it's not known, so it makes an arbitrary decision. That's forwarded up to a firewall worker. Firewall worker processes that packet, executes that packet, looks in the rule base, see if that packet is allowed. It is allowed, updates its own local connection table, and then will update the dispatcher about that connection. Firewall worker number 2 obviously processes that connection, said it's up the IP stack. The IP stack is going to do the routing, makes a routing decision, sends it off on its way. Next, another packet comes into the dispatcher. The dispatcher looks in the dispatch table. Is that packet in the table? No, it's not in the table. So let's assign it to arbitrarily. I'm going to assign it to Firewall Worker 1. Firewall Worker 1 is in the rule base. There is a rule allowing that traffic. So it processes it and updates its connection table about that connection, and also updates the dispatch table about that connection. So now the dispatch table knows about that packet that was processed for Firewall Worker 1. That packet on Firewall Worker 1 is then sent up to the router. The router is going to make a routing decision. Again, forwards that packet off on its way. So let's take a look at what happens when another packet comes in. Packet comes in to the dispatcher. The dispatcher looks to see if that packet is known in the dispatch table, and it finds a match, and it finds that it was signed to Firewall Worker 2. Lookup was found, and then the packet is forwarded to Firewall Worker 2. Firewall Worker 2 is going to execute, run that packet, and obviously it knows about that connection because it has it in its own connection table. So it doesn't have to go to the rule base to see if there's a rule allowing it. We save some cycles here because we already know about the connection. That connection is then obviously forward up to the router. The router is going to route it. But the point I want to make here is we don't need to look in the firewall rule base anymore. The first packet we looked in the rule base. The second packet we look in the local connection table. Local connection table knows about this packet, and it's processed and forward out on its way. One advantage of using CoreXL is that you can have parallel cores executing code simultaneously at the same time. So packets are coming in to different cores. Dispatcher is acting like a load balancer. It makes a decision where to assign the packets, and it's going to assign them to the CPUs that are not being utilized. So 3 cores get 3 simultaneous packets. They process and forward those packets. Using CoreXL, you get performance by having parallel processing. The second advantage, and I'll explain it here, is when the packet comes into CPU 1, another packet comes into dispatcher, makes a decision Firewall 1. They both execute those packets, forward it on its way. Now what happens if the dispatcher was to assign that packet to an incorrect core? It would be dropped out of state because Firewall 2 does not know about that connection. So the other advantage you get here, performance-wise, is that by having the global dispatch table, you're assigning the packets to the correct cores. Part of the goal of the dispatcher is to be able to make the packet sticky, making sure that the connection is always forward to the appropriate core that knows about it. Because if it doesn't, then you lose performance. The third method in relation to performance is what we call data locality. Data locality, in essence, means make sure that the data is local. What does that mean? It means all appliances have memory, and so memory is where actually the connection tables are stored. So this connection table that we have here is actually stored in memory, and this connection table that we have here, this connection table is also stored in memory. It's not the CPU that has this information. When the packet comes into the CPU 0 looks in the global dispatch table. If it knows about it, great. If it doesn't, it forwards it to CPU, which processes that connection and updates the connection table. Updates the connection table, it's actually updating it into the memory. In the CPU, you also have cache. You have cache 1, and then you have other caches, smaller caches 2. Let's assume we have 3 cache. And so to speed up the CPU process, information that the CPU needs to execute, it first looks into memory, gets some of the code, not the connection table, but the firewall codes. And it will take this firewall code, it will process that information according to that packet, the rule base, etc. And also updates some of the cache with information that it received from the memory. The same thing when it's processing that connection, it updates some of that information that it used to process in the cache. Next time packet comes in, it looks to see where to assign it. The global dispatch table knows about it, so it says forward it to CPU 2. CPU 2 receives that packet. CPU 2 needs to do some calculations. CPU 2 needs to remove some information from memory. It needs to call firewall code. It needs to call the connection table information to see if that connection is there. Right? And so it checks, before it gets to the memory, it checks the cache and it finds firewall code. It doesn't have to go to the memory, so finding things in cache is a lot faster than actually going to memory. So you have performance improvements by using cache. And so data locality in essence means to keep the same connections going to the same CPU, so we can take advantage of the data that's local on those CPU's caches. Okay, next thing we're going to talk about is Core Affinity. What does Core Affinity mean? Core Affinity in essence means we've unbound and rebound instances and dispatcher to different cores. Let's take a look here. Here I have 4 core systems. I have CPU 0, 1, 2, and 3, and look at CPU 0 is running the dispatcher, CPU 1 is running Firewall Worker 2, CPU 2 is running Firewall Worker 1, CPU 3 is running Firewall Worker 0. And so let's assume here that we have a lot of traffic. A lot of traffic is coming to the dispatcher. All traffic that comes to the NIC is going to be processed by the same CPU that is assigned to the dispatcher. The dispatcher and the NIC are using the same core, the same CPU. And I was saying if you have a lot of traffic, so a lot of traffic is coming to this CPU constantly, and you have 3 firewall workers, and you run some commands to verify the performance of your CPU, and you notice that CPU 0 is using maybe 5% is idle, meaning it's using 95%, and the other CPUs are maybe 25% each. You know that the dispatcher is being overused and you have a lot more resources on the other CPUs. So CPU Affinity, we can remove a firewall worker from one CPU and bind the dispatcher to 2 CPUs. So now the dispatcher will be running on 2 CPUs. Let's take a look. I have a diagram here that shows that a little bit better. And so just know that the NIC cards, all the traffic coming into the NIC, is going to be assigned to the CPU that's running the dispatcher. The dispatcher is actually being run on 2 different CPUs. So the NIC will send traffic automatically to the different CPUs. The CPUs will process that information from the NIC. The dispatcher will look and process that information from either NIC, and obviously we're sending these packets to firewall workers too. And so what we've done here, CPU Affinity, in essence means we've unbound and rebound instances and dispatcher to different cores. Here's another example. Let's assume that you've run some top commands and you've identified that one of the processes, FWD, for logging is using a lot of CPUs. What you could do is assign a process directly to its own CPU. So this is what we call CPU Infinity, and there's only a few processes that you can do this to, but FW1 is one of the processes. CPU Infinity is how you bind different processes like firewall process or different dispatchers or different firewall instances to different CPUs. Let me give you another example of that in the next slide. Here I have 8 cores, and my 8 cores, I have 1 dispatcher, and the dispatcher is very busy. It's processing a lot of connections. So what I could do is I can bind 2 CPUs to the dispatcher. I can remove one of the firewall instances. You can actually unbind firewall worker 6 from the CPU and attach the dispatcher, so the dispatcher can run on 2 CPUs, like so. So now I have the secure network dispatcher. That dispatcher is running on 2 separate CPUs, and it has the global dispatch table. So the dispatcher is sharing 2 CPUs, and the global dispatch table is also sharing 2 CPUs. And traffic coming into the NIC, it's going to be assigned to the same CPUs that are running the dispatcher, so traffic will be coming in to the different CPUs to processing. The different CPUs will then assign the different traffic to different firewall workers. Now I can even go further in this. So here's an example where I used 4 CPUs to run the dispatcher. So this is where I have a lot of traffic coming into the NICs, multiple traffic, and so I need multiple CPUs to be able to process all the traffic that's coming into the NICs. So the NICs again are bound to the same CPUs that are bound to the dispatcher. And so now I have 4 CPUs to be able to process traffic from the NIC, and also 4 CPUs to be able to process traffic in relation to the dispatcher and updating the dispatch table. Again, it's one dispatch table that's shared amongst all the CPUs. And so the traffic are coming into the NIC, coming into the CPUs. The dispatcher makes the decision, updates the dispatch table, and forwards that information to the firewall workers for them to process and look in the rule base. Okay, so here's an example where I've unbound firewall workers. So now I only have 4 firewall workers in this case, 4 firewall workers, but I have 4 CPUs that are being utilized for the dispatcher. And this will make a little bit more sense when we talk about CoreXL, but right now I just want you to understand what CPU affinity meant is how you bind different processes, different kernels to different CPUs, either firewall instance or the dispatcher. So another terminology I want to discuss is SIM affinity. But in essence, what SIM affinity allows you to do is bind different ports on the NIC. Let's say I have 4-port NIC and I want to assign 2 ports to be used on this NIC or 2 ports to be used on this CPU. So by default, you have the automatic interface affinity, automatic interfaces. Traffic comes in automatically to the NIC cards, and it will be automatically assigned to different CPUs automatically depending on how busy the CPUs are. But at the same time, if I want to do manual configurations of where I can assign the traffic, and so if I have 4 ports, and let's assume that one of these ports is external port, and so a lot of traffic is coming into my external interface, coming into this port, which is my external interface, and so I see traffic going all over the place, so I might want to assign this specific port to only and have its own dedicated CPU, and have other 3 ports being assigned to a different CPU. So my internal interface, my DMZ, and maybe my branch interface, there's not as much traffic as my external interface from DDoS attacks, etc. And so I'm assigning one interface to a specific CPU. Another example might be if I had, let's use 2 ports here, and I had a port that I VLANed in multiple VLANs. So VLAN 1, VLAN 2, VLAN 100, so it's 100 VLANs coming in, and so this port is very busy, it's using a lot of traffic, and so I might want to have a dedicated CPU for this specific port, so I can bind that port to that specific CPU, and the other ports will be bound to other CPUs. And so this is what we call SIM affinity. SIM affinity is when we bind specific NIC ports to specific CPUs. And multi-queue. What is multi-queue? So multi-queue is where I have, let's say I have a 2-port on the NIC. So this might be a 10 gig port, and this is also a 10 gig port. So I've VLANed it in multiple VLANs, but I only have 2 ports. But I have a lot of traffic because these are 10 gigs. So I have 4 CPUs that I can assign to processing. But I only have 2 ports. Usually it's going to be 1 RRQ per port. So an RRQ is going to be assigned to a specific CPU, and this will have also an RRQX, RRQY assigned to a specific CPU. So I have 2 additional CPUs that I could use for traffic, but I only have 2 ports. So what I could do is have an IRQ bound to different CPUs. So IRQX would be here, and IRQX also bound to CPU1, and IRQY and IRQY bound to CPU2 and CPU3. So all traffic here will be assigned to these 2 CPUs. All traffic coming into this port will be assigned to 2 CPUs. So 2 CPUs could process traffic from 1 port. So this is multi-queuing, is you have 1 port and going to multiple queues for the CPU, because the CPU have queues. So traffic is coming into the queue waiting to be processed, and when the CPU is ready, it's going to process that connection. Same thing on the other side. And so this is why we call multi-queue, because you can have 2 queues bound to 1 port. Okay, the next topic I want to discuss is, well, what happens if you have only 1 core? If you have only 1 core, it stands to reason that you cannot have CoreXL. But if you had 2 cores, where is the dispatcher and where is the firewall worker? Let's take a look at this next diagram here. I could, in essence, have a dispatcher running on 1 core and another firewall worker running on another core, but that would not work properly. You would not get the performance you need. And so what you could do when you have 2 cores, you can have one dispatcher that's bound to 2 CPUs and 2 firewall workers that are bound to the CPU. So you're sharing 2 CPUs amongst the dispatcher, and you're sharing the CPUs amongst the firewall workers. And so let's recap this module. First, we talked about multi-cores. Multi-cores was a way to get more processing because of the limitations on physical hardware. And then we talked about the need for CoreXL. We talked about originally R65 introduced CoreXL plus the Linux kernel to be able to run CoreXL. And then you needed to purchase the CoreXL, so you need a license to be able to use the CoreXL to unlock the cores. And so if I have 8 cores and I only purchase CoreXL for 4 cores, I can only use 4 cores. And later on I can purchase a different license and I can purchase 2 more cores, a license to allow me to use 2 more cores, and another license to use 2 more cores, so I can have a total of 8 cores. And if I have hyper-threading is supported starting with Gaia, and Gaia, when it's running a 64-bit operating system, that means that physically you have 8 cores, but logically you have double the amount of cores, so you can have up to 8 times 2 is 16, so you have 16 cores. 8 are physical and 8 are logical cores, and so you can use the physical and logical cores to be able to assign information. And then we talked about the firewall components. The firewall components is the firewall instance. The firewall instance is duplicated in its own independent firewall and running on different cores. And we also talk about the other component, which is the dispatcher, and the dispatcher, also called the secure network dispatcher, is where it keeps track of all the connections in the global connection table. And then we discussed how CoreXL works, how a packet comes into the dispatcher. A dispatcher makes a decision to where to forward that traffic, forwards it to one of the firewall workers. The firewall worker then processes that connection, looks in the rule base, finds a rule, sends that packet to the routing for routing purposes, and also updates the dispatch table about that connection. And we talked about performance implications running CoreXL. We talked about data locality. Data locality in essence means to keep the same connections on the same CPU, so we can take advantage of the cache that are built into the CPUs. And we also talk about the dispatcher, making sure that the dispatcher keeps the connection assigned to the same cores. Then we talked about core affinity. We talked about CPU affinity. CPU affinity is where we assign different processes, different dispatchers, firewall instances to different CPUs. So I can assign firewall workers to 2 CPUs. I can assign firewall workers to 4 CPUs. I can assign dispatchers to 1 CPU or 2 or 4 CPUs, etc. And also we talked about SIM affinity. SIM affinity is where you can assign different ports to different CPUs. And we also talk about multi-queuing. Multi-queuing is where we assign a specific port to more than one queue that's running on the CPU. And so we come to the end of this chapter. I hope that this information was informative. Thank you once again for joining me in Checkpoint Training Bytes. We'll see you next time. Bye for now. Shalom. Checkpoint. We secure the future.